Hey, I'm going to talk about Neon today. So Neon is a new storage system that we've been building for Postgres in the last year or so. It's also the name of a cloud service that we will operate, and it's also the name of a startup company that we work for. So the story started about a year ago when me and Stas Kelovich, the co-founder, and our CEO, Nikita Shamgunov, decided to found a company to build this new storage system for Postgres. And we started building this about a year ago, and I'm going to explain where we are right now. But to get started, so in a traditional Postgres setup, you would have Postgres running, and Postgres manages its local disk. It could be a local SSD drive, that's typical nowadays, or it could be an EBS volume or spinning Rust hard drive. But the point is that Postgres manages this storage. It's kind of attached to Postgres itself. It could be a SAN drive or something else, but it can't be shared with other Postgres instances. It's owned by the Postgres, and Postgres manages it as a local file system. Now that's simple. I mean that works, and you get good performance out of that. Nothing wrong with that. But things start to get a little bit more complicated when you start to do cloud stuff. I mean, first of all, you would normally want to have backups. And the typical setup nowadays in the cloud is that you have some kind of cloud storage, Amazon S3 or Google Cloud Storage or Wasabi or something else that provides you with cheap storage. And you take your periodic backups, maybe once a day, once a week, whatever suits you. And then you also stream all the write-ahead log to the cloud storage so that you can do things like point-in-time recovery and stuff like that. There's a lot of good tools for managing all of this. And this is your typical setup nowadays. It gets more complicated when you also have a read replicas. Like you might have the Postgres primary server, and you stream all the while to the Postgres replica, and now you also have something like PG backrest or something to manage your backups and WAL archive. That's fine. But this starts to get more complicated when you have a lot of these read replicas. You have primary, you need to manage which is the primary, you need to manage the failovers and stuff like that. And you also have a lot of, you have many different copies of the same database, essentially. You mean you have your copy in the Postgres primary, but the replica will also have a copy of the database. This gets complicated if you have a large amount of data. If you need to set up a new replica and you need to copy 100 gigabyte or a terabyte of data to do that, that's kind of slow. So the key idea of Neon is to separate the compute and storage. And so what does that mean? So in our model, Postgres runs as it always does. It's the same Postgres source code running, but it doesn't manage the local disk anymore. So we've separated the storage side to what we call the Neon storage system. So Postgres runs, and whenever you modify something, it generates the write-ahead log. But the write-ahead log is streamed to the Neon storage system, and the storage system processes the log and figures out what to do with it, and it stores it. And then when Postgres needs to read a page, it doesn't have a local disk. It doesn't have any local storage. So it will send a request to the Neon storage system to read a page. And Neon still makes use of cloud storage behind the scenes, so it will still upload the stuff to cloud storage. You get all the benefits from that. But the point is that this replaces your local storage and backups and WAL archive. All of that is handled by the Neon storage system. One way I like to think about it is that it's like a SAN on steroids. So it's a SAN in the sense that it can be shared by multiple Postgres instances, and it manages the space between them, and you attach your Postgres instance to it. But it knows about the Postgres write-ahead log format and the page format, and it allows you to do some cool stuff with that. We didn't invent this. There's a lot of systems nowadays that try to do similar things, and quite successfully. The first one was Amazon Aurora. Google just announced the other day or other week that their Alloy DB, which is the same basic idea. They also separate the compute and storage. Then there's others. There's PolarDB. Microsoft has been doing this for a while with their Hyperscale for SQL Server. Snowflake is doing this for data warehousing, and they're growing very quickly. And then the single store and many others probably nowadays. So what are the advantages of this? First of all, you don't need to do this lengthy while recovery. In a traditional Postgres setup, or most databases work the same way, if you need to recover your database, you take the last backup, which could be a day old or a week old, and then you take all the write-ahead log from your WAL archive and you replay that. And that can take a long time. If you have a large database and there's a lot of activity in it, this can take hours just to do the WAL replay. Now with Neon, Neon storage system takes care of the WAL recovery for you, and it does that continuously in the background. And it can do that page at a time. So you don't need to recover the whole database. Instead, you can spin up the new Postgres instance immediately against the storage system, and Neon will do the write-ahead log replay in the background or on demand. So when you try to read a page, or when you do a select star from a table, it will do the WAL redo just for that table and just for the parts of the table that you need. Similarly, if you need to set up a read replica in a traditional system, you do the same thing. You take the last backup, you replay all the log, and that can take a lot of time. It also requires a full copy of your data. Your standby will have a full copy of your data. But if you have a 1 terabyte database, you need another 1 terabyte of storage for that, and you need to provision for that. With Neon, this starts up instantly, so you don't need to do this WAL replay because it will be done on demand if needed. It's also very lightweight because the read replica can share the storage, so it just attaches to the same storage, and both the primary and the replica can read from the same shared storage. So this doesn't look very interesting if you just have a primary, but if you start to consider all of this other stuff you might want to do with Postgres or your database, you start to see the advantage of this storage system. So you have the primary. You can quickly kill the primary, and you can create a new primary because it can be a Docker container. It can be something that it doesn't have any local disk, so it's very easy to just kill it, recreate it if needed. You can also have these read replicas attached to the same storage system. Neon can also do point-in-time recovery because it replaces your WAL archive. It keeps all of the write-ahead log in its own format that's like indexed and ready to be accessed at any time. So you can attach like a time travel Postgres instance to the same storage system without having to make a copy, without having to restore a backup. It also allows you to do what we call branching, so you can do a copy on write branch of your data, which is very useful for if you want to try some change before you commit to doing it in production, or if you want to make a copy of your database for testing purposes, you don't actually have to do a copy. You can just create a very lightweight branch of that. Now, how does this work? If you take a closer look to the storage system, the input to the storage system is the WAL stream at the top. So you get the WAL stream coming from Postgres. It first gets streamed to what we call the WAL safekeepers. And there's multiple copies of these safekeepers running on different nodes. And there's a quorum algorithm going on there. So the point of the safekeepers is to provide durability. So when a batch of WAL comes in and you commit your transaction, we don't acknowledge the transaction as committed to the client until it's been flushed to disk in all of these safekeepers, or a majority of the safekeepers rather. So that provides you the durability aspect. But kind of the more interesting part or more complicated part is the page server. So when the safekeepers have stored the WAL durably, it gets streamed to the page server. And the page server contains a lot of code to process the WAL, and if you peek into that, so it will receive the WAL and then it will process it into its internal format, which is the same write-ahead log format, but it's indexed by page, so we can easily look up the WAL records for a particular page. And the output from the page server is this get page request. So whenever Postgres needs to read a page, it sends a request to the page server, get page number 100 of this relation or something like that. So the page server will process the request. It will reconstruct that version of that page It will perform while redo for that particular page if it has to, if it didn't have it materialized already, and then it sends the request back. So one interesting aspect here is that we actually run a copy of Postgres inside the page server too, but that's just to do the while redo. So we use the Postgres while redo functions to do the recovery of the pages as needed. Finally, the page server also uploads all the data to cloud storage. So actually one way to think about it is that the page server is just a cache of what's ultimately stored in the cloud storage. So that gives you a lot of flexibility. Like if the page server goes down, we can reconstruct all of the data from the cloud storage and download it as needed. So the page server is really the heart of the system. It receives the while, processes it, and there's a lot of magic in the storage format. First of all, it's based on immutable files. When the while comes in, it's processed and it's stored in these immutable files. We don't ever go and update them in place. We just keep accumulating more data in them. And it's kind of similar to an LSM tree, like a log structured merge tree, in that you have an in-memory layer on the top, and it collects data and indexes it, and then when it fills up, it gets flushed to disk to a new file, and so forth. And then there's a lot of compaction and garbage collection activity happening in the background to reshuffle the data. And there's a lot of heuristics in where do you store the while records, and when do you actually perform the while recovery for a particular page, when do you decide to materialize it, and so forth. So from a Postgres point of view, the kind of interface that Postgres sees is this get page network call. So what it will do, it will find the last materialized version of that page, and then it will replay all the while records up to that for that page up to the point that you requested, and it will send the materialized page version back. So the important point here is that the get page request contains the information about which block is it, like which table, which index, which relation, which block number within that table, but also the LSN. The LSN is like the point in time, and this is what allows us to do time travel query, for example. You can just launch a new Postgres instance and set a setting saying whenever you read something, you send this LSN as part of the request. So now your Postgres instance will see all of the data at an older point in time, for example. I mentioned branching. So this is a feature like Git branching but for data. So this can be very useful for CI/CD workloads, for example. You can create a branch of your production database, and you can run your CI against that branch. And when you're done, you just drop the branch. Or if you want to try like a schema migration, for example, you can create a branch, try it there, see if you're happy with it, and before you do that on your production database. So how does this actually work? I prepared a small demo. Here we go. So the way this works is that first of all, now this all runs locally on my laptop. I'm going to create a new page server, a new repository, start it up, and I'm going to launch a new Postgres server running against the storage. Here we go, and you can see that it's running. Now I'm going to connect to it. You can see the connection string here, and it works just like any Postgres instance. You can create a table, create a table called PGCon, insert the value there. Here we go. And so far so good, nothing special here. It's just Postgres running against the Neon storage system. Now, the next cool thing is that you can do these branches. So I'm going to create a branch of the database I just created. Let's call it the future. There we go, we have a branch. And as you can see, this was very instant. It happened instantly. It doesn't copy any data. Well, there wasn't much data to copy with anyway. It was an almost empty database. But the point here is that this would work just as fast, just as well, even if you had a terabyte database. It doesn't copy any data at this point. but now we have a branch. And now that we have a branch, we can list it. You can see that there's the main branch and there is the future branch. Now, what you can do next is launch a new Postgres instance against the branch. So I'm going to launch a new Postgres server running against this branch now. And there it is. It started up immediately. And you can connect to it and you can see the same data as was there that I inserted before the branching. But now what you can do is to insert some more data to it. For example, here we go. And to demonstrate the point-in-time query feature, I'm going to get the current LSN of the point here. I'm going to use that later and insert some more values. Okay, there we go. Now that we have the branch and we inserted some new data to that branch, what we can do next is to start. You can start a new Postgres instance running against an older point in time. So I'm going to demo the time travel query. So let's start a new Postgres instance that will see the data as of that older point in time. So this is a bit complicated with the syntax, but we'll keep improving on that. So let's see, what was the LSN here? No, it didn't work. Oh, PG start, here we go. So it started a new Postgres instance running against that older point in time. So we now have 3 Postgres instances running. There's the original one on the main branch. And then we created the branch and we have 2 Postgres instances running against that branch. So you can see the LSN here. This is the one at the tip of the branch, at the end of the branch. But we also have now this new Postgres instance running at the older point in time. So if we connect to that and do a select star from the table, we can see all of the data that was inserted up to that point. If we scroll up, you can see that we inserted 2023, 2024, and then I looked at the LSN at that point and inserted some more rows. And this new Postgres server sees only the data that was inserted before that point in time. Now, dealing with these LSNs is a bit complicated, but we can also do this based on timestamps. So you can give a timestamp, launch a new Postgres instance that runs against like 5 p.m. yesterday, for example, if you want to do that. And it starts up immediately. As I said, it doesn't need to recover any data. It doesn't need to do while redo. It just launches immediately. So that's for the demo. So what's the current status of the project? All of the code is on GitHub. If you want to go and take a peek, it's there. It's Apache 2 licensed. All of this page server, all the safekeeper, the storage code is written in Rust. There's also a bunch of tests written in Python and so forth, but most of the code is written in Rust. And it passes the Postgres regression tests currently with tiny modifications. There's some stuff like table spaces that don't really make sense with this storage system, and so we had to modify those. But basically all the stuff that you would expect to work do work. All the index types work. This works below the access method layer, so all of the index types work without modifications and so forth. So maybe one interesting question is, why did we choose Rust for this? Well, it was mostly because the page server and this kind of the storage system is multi-tenant, so we want to run this service on the cloud for everyone to use, and we want to share the resources. And for that, it was really important for us that there wouldn't be like memory corruption issues. Like, we don't want to accidentally leak the data from one customer to another, basically. And so we wanted to have a memory-safe language to write this in. So I can talk more about why we chose Rust, but that's been a fun choice. I mean, being a Postgres hacker and used to writing C code, it's a nice language. Maybe that's a topic for another presentation. We have a bunch of to-dos still. We currently don't have support for read replicas that follow the primary. So you can launch a new read replica against a point in time, like I did in the demo. You can't currently have one that follows the primary, but that's almost there. We actually have a pull request for that written already, but we haven't merged it. We also don't do sharding or scaling the storage yet, so you're kind of still limited by the amount that you can fit in a single box there. But in the future, this architecture would allow you to also shard very easily. Just have multiple page servers running, and each one handles like a portion of the key space. Similarly, you could very easily imagine scaling that. If you need more I/O resources, you can just have multiple copies of the page server the storage running. But we haven't done that yet. But that's a future thing to do. We also have a lot of performance work left to do. I'm not sure how well this would still work with the larger databases with more volume, but that's something we will keep working on. If the architecture is sound and it allows you to do those things, but we have to figure out the right heuristics for when do you materialize and so forth, and a lot of low-level optimization work left to do. Also, we don't do the on-demand download from cloud storage yet. We just do that for the whole database currently, but that's also something that's simple to add later on. Now, one interesting question is the Postgres code. How much did we have to modify the Postgres code in order to do that? First of all, the goal is that Neon, you could run just regular unmodified community Postgres against the Neon storage. We're not there yet. So the main hook where we plug into is the SMGR API. That's the storage manager API in Postgres. That deals with reading pages and writing pages, and that's where we hook into. Now that's not a really extensible API in Postgres. It's an internal API that was put in there back in 1995, but there hasn't actually been another implementation of that API ever since really working. But that is where we're hooking into, and so we need to clean up a few places here and there that kind of bypass that API and plug into it. That's one thing. The other big thing that we need to deal with is stuff that don't go through the buffer cache and don't go through the storage manager API, like a PG exact, that's the seal of the commit log, PG subtrans. There's a few other of these SLRU structs that currently they have their own storage mechanism. Kind of the plan for that is that we should also make those more regular and store them the same way through the same storage API as these other things, and that will solve the problem for us. It would also be nice. There's been discussion on the mailing list about doing that anyway, because that would allow you to use the same buffer cache for all of these SLRUs. Another funny thing that we need is to track the LSN of the last evicted page in the buffer manager. That is something that Postgres doesn't have a need for, but we needed that for performance in Neon. One funny question is, what do you do with unlocked tables? And we actually had quite long discussions about this internally. Like, what does it mean to have an unlocked table in a system like Neon? Because there is no local disk. So what do? Well, the way it works currently is that if you create an unlocked table, it doesn't go to the storage system, and it is actually stored locally with the Postgres instance. Now, the downside of that is, of course, that if you crash or if you just shut down Postgres, your unlocked table goes away. But that's kind of that's the deal with unlocked tables in general. So I think that's okay. I mean, the other opinion is that that's not very nice, and also if you don't want to have a local disk, then unlocked table, where do you store it then? Maybe you have a separate a volume for that or something. But that unlocked tables, I mean, that's not a big deal in general. So kind of the goal here is to run just unmodified Postgres, and also allow people to run whatever extensions they want. I mean, this doesn't limit you to, as long as your extension doesn't touch the very, very low level I/O routines, any extension will work with this thing. We already tried Citus just briefly. and found some bugs by trying that, but we fixed them, and now it works. Just as an example of things that do work. Also, one thing that annoys me with many cloud providers in general is that they don't give you access to run your own modified versions of Postgres or your own extensions. So we want to be better than that and actually allow you to run whatever random modifications and extensions you want. But that's in short. The kind of the other part that we have been doing, I mean, that's about the storage system. That's the code that's out there on GitHub. Now, the other big part that we have been doing in parallel with this work is to actually build a cloud service that operates this thing for you. So we do have a cloud service now that kind of it's what we call early technical preview. And so if you go to neon.tech, you can sign up, get an invite code. And once it's stable enough and it works well enough, we'll remove the invite code system and allow anyone to go in. But the point is that you can go to the cloud service and we make it super easy to create your own Postgres instance. It's serverless, which means that when you connect to it, we spin up the Postgres instance against the Neon storage system. And if it's idle for 5 minutes, that's the timeout currently, we just shut it down. We shut down the Postgres instance. And then when you try to connect again, we will launch it again. So it runs in a Docker container managed by Kubernetes. And this stop and start is very fast because there is no local disk. It doesn't have to restore any local data. It just connects to the storage system and it's up and running instantly. I think the startup time is about half a second right now. And most of that goes into spinning up the Kubernetes and Docker image and all of that stuff. We provide a free tier, so if you want to try this out, I think the limit is 10 gigabytes of data currently, and an API for playing with that. One nice party trick, you can try this directly with PSQL. If you try that, you will get a prompt to log in with your GitHub account. But after that, it drops you into a Postgres database and it's up and running. The invite code is there. That's all I have for today. I will be here for Q&A session. Send me any feedback. Thank you.